with a group of Kadowaki, and that's basically the list of collaborators. Okay, so in previous talk given by Yegor Babaev, he mentioned briefly this interesting new possibility which appears in multi-component superconductors. Briefly. No,
because I'm coming from the York Institute, and the rule of the talks was the talk starts at 4 o'clock, and the cutoff when the last subway train leaves. Okay. And I think it almost was all the way to cutoff.
So, but I will start to stay well on time. So actually, otherwise he can unplug my computer at any moment. And all right, so you have in single component superconductors basically this well-known division depending on the ratio between two fundamental parameters, penetration depth and coherence length. So you may have type 1 superconductivity, which was discovered first, where you have a direct transition from Meissner to normal state, and you have also the second type of superconducting materials predicted by Abrikosov, for which he was awarded Nobel Prize a few years ago, where you go from Meissner state to the normal state via so-called Abrikosov vortex state or mixed state. So if you take typical type 1 superconductor and zoom in into the pattern of field penetration, then very often you see these macroscopic stripes, and actually this is an intermediate state, and in this case you have a coexistence of normal and superconducting stripes here. So on the other hand, in type 2 superconductors you have actually this quantum state predicted by Abrikosov, where applied flux is split into quantized entities. Each of them is carrying exactly one flux quantum, as visualized by these pioneering experiments of Essmann and Troible in the 60s. So each white spot, black spot, corresponds to one flux quantum, which later on was visualized by using scanning tunneling microscopy, and these black dots are quartzes. Yes?
I'm simply curious because I simply don't know. Was it ever measured that it's one flux, one unit?
Yes, of course. So it's very easy. You know the area, you know the applied field, you know total flux, okay. And then you can exactly calculate how much flux per unit area, and then from there to calculate the distance, and that matches perfectly well with what you expect. But doubly quantized watches are not excluded, and actually they might appear in the vicinity of this crossover point between type 1 and type 2 superconductivity. And then, this is indeed a special case when copper is very close to 1 divided by square root of 2, and then very often you see very interesting example of coexistence, that you have Meissner areas which are surrounded by the vortex state. But this happens in single component superconductivity only very close to this critical point, lambda divided by xc equals to 1 divided by square root of 2.
I think it's actually in that case it comes from repulsive interaction with two length scales, with long range repulsion coming from stray fields.
Yeah, this could be indeed like that. But okay, I've just defined it formally, whatever the reason for that. Then in already 59, Ari Suhl, Matthias and Walker, they considered this situation that in principle you may have several bands crossing the Fermi level, and then you may have formation of Cooper pairs in two sorts of condensates, which can be either totally decoupled, then you have simply two different TCs, or if they are weakly coupled, then you will follow this dashed line. And this is actually the prediction of this coexistence of two other parameters in superconducting materials. So then a few years ago, and we've heard already in this short talk, which was well on time by the previous speaker, that actually you can introduce a very interesting situation, which was coined by Babayev and Spite as semi-Meissner state. Then you can actually consider two component materials where you can consider type 1 conditions for the first subcomponent of the order parameter for psi 1, and simultaneously type 2 conditions for the component psi 2. And then what I'm going now to show you, what will happen actually in this interesting state, and I will present also some vortex visualization experiments which show that actually here, in this case, you do not have conventional abricosal vortex lattice, but rather you have rather exotic patterns of vortex clusters, vortex chains, vortex stripes, etc. Another example was proposed, I think, in the review written by Alex Gurvich. He was sitting here, but now he's sitting in a different place over there. Yeah. Where he considered two different superconductors in his model. It was not considered specifically that they may be type 1 and type 2, but you can consider simply two different superconductors which are coupled via an insulating layer. And that was also mentioned during discussion, actually, that you can imitate this two-component physics if you make artificial sandwich structure.
Is it important that they are different? Why not to do them the similar conductor? In any case, you have
then you, I want to achieve eventually two different regimes, type 1 and type 2. So
because you need different...
I just want to do it like that, okay, yes.
Okay,
but of course you can take the same material, you can make multi-layer.
No, I see type 1 and type 2.
Type 1 and type 2.
Thank you.
Okay, and since this is quite abstract scheme, I can write whatever I like here. Okay, so I can like here ferromagnet, I can like antiferromagnet, whatever you want. So then if you take indeed MGB2, this is what should be called natural to get type 1.5 superconductor. At the Fermi surface, you do have contribution from pi bands and from sigma bands, and pi and sigma bands are indicated here. So you do have two bands, and correspondingly, if you study superconducting gap with scanning tunneling microscopy, then it has been reported by several groups practically simultaneously that you do have in tunneling spectra, instead of nice well-defined single gap material, you always have two gaps here, one gap smaller, another gap is bigger. Very much so here. So the first gap is about 2 milli-electron volt, the second one is around 7 milli-electron volts. So this is a well-known property of MGB2. And then if you have
the estimate of Johnson energy in this case.
So here coupling is not that strong actually between the two bands.
Like
but
1/3.
Yeah,
1/3.
it's certainly much less than one, but yeah. All right. So then,
So
if you have,
this actually, is it obvious that it's type 2 and 1 and type 2?
so I'll show it on the next slide. Okay. So then if you have actually two bands, then you can get regular interband processes to form pairs like that. So you keep the color the same, or you can mix up the colors or mix up the bands. Then you have interband formation of the Cooper pairs. And if you follow the evolution of these two gaps from scanning tunneling microscopy data, then they are extrapolated, although here the error bar is quite big, so it's not clear whether these two TCs originally are the same, corresponding to two order parameters, or they are quite close, or maybe they are quite separate. Then you have proximity-induced superconductivity in the second gap. But in general, you expect that these two partial TCs can be different. So then, again, this has been
the
mentioned.
absence of Johnson coupling, right?
Yeah. Yeah.
So it is 1/3 of the smallest one.
It's 1/3, but I think the estimates are different, but it's between 0.1 and 0.3, something like that.
Yeah. So there is no way to have two TC.
No.
No, this is excluded. It's really, this is completely clear that you do have one force. So then you have to mix up the other parameter to introduce this mixed term in Ginzburg-Landau, as again was introduced by the previous speaker here. And then basically you have a two-component Ginzburg-Landau theory with this term. And then actually electrodynamic response of a superconductor will be determined by effective lambda, which is calculated roughly 1 divided by lambda effective squared is approximately 1 divided by lambda 1 squared plus 1 divided by lambda 2 squared. And still you will keep this psi1, psi2. And in principle, although the response is determined by that, but I still have a memory of these two sublambdas. So in principle, formally, I can define two ratios, lambda 1 divided by psi1 and lambda 2 divided by psi2. And from that point of view, I can formally define type 1.5 regime. But of course, everyone knows that actually there is a single lambda. But like a single child always has two parents. Okay? So it's very much so here. So although in a few comments I've been criticized that I dared to speak about two lambdas. Okay? So who cares? So I dare to speak about two parents or the single child. All right, so then if you do certain transformation, then you can reduce Ginzburg-Landau functional to this form. Then you have to introduce effective kappa. And then actually in the vicinity of TC, this Q diverges, goes to infinity, and to keep the whole physics well determined, you have to reduce everything back at the phase line to single component physics. So if you want to eliminate this unpleasant divergence, then at the phase boundary you have to take a single order parameter. But the kappa will be in any case determined by the contributions from two subbands. There is no way to avoid it. So therefore, so what I will show that in actually in type 1.5 superconductors you have rather exotic vortex-vortex interaction, and in a naive picture it can be considered as a sort of a compromise between vortex-vortex interaction in type 1 and vortex-vortex repulsion in type 2. And in two-gap superconductors, important point is that you have a much broader range of parameters where this interesting regime can be realized, contrary to single component superconductivity where exotic vortex-vortex interactions appear strictly in a very close vicinity of this crossover. All right, so now with that reduced kappa, you can...
Victor,
yes?
if I have a repulsion for both vortices,
yes.
then will be conventional type 2 superconductor, there will be nothing interesting.
You will see evolution of vortex-vortex interaction force, which is just given here for two different efficient kappa, which I have introduced. So if I take, for example, this case, when kappa, effective kappa is 0.65, so it's type 1 regime, but I can have a very different band parameters. And then I switch Johnson coupling on, and then if you see, I have this coupling between 0.1 to 0.4, then vortex-vortex interaction here corresponds to attraction, but there is additional minimum here.
So this is corresponds to the region away from TC, not in the Ginzburg-Landau region, because that Ginzburg-Landau region corresponds to Q is greater than.
So this is a very interesting question where actually Ginzburg-Landau limit is valid. So from experimental point of view, we managed to apply very successfully Ginzburg-Landau theory from TC to 0 without any problem. From the point of view of theory, I do know that this theory was developed, strictly speaking, to describe the situation at the phase boundary. But anyway, this one is, how to say, this is a philosophical question. TC, T divided by TC minus 1 modulus here is 0.99. So how do you qualify? Should I use Ginzburg-Landau or not? The question is 0.01,
No, then Q is
much less than 1 or not?
no, then Q is not 0.1. Q is more like 20.
No, that's not correct.
If you take parameters of MGB2, then
No, this I will come to parameters of
You
MGB2.
can take a London theory from one band and
No,
you can have result also Allenberger.
So this is a question,
yeah,
Igor. I think this is a question, what do you call close? So I'm claiming here, if I take T divided by TC, in the range 0.9 to 0.99, so then I form 1 minus that, I end up with 0.100 or 1/10, and I dare to claim that this is still much less than 1.
sure.
Okay,
The
so
question is,
for me no problem.
No, the Q, which is equal to 20, was it obtained with the parameters of MGB2 or
This
is it a
one.
model?
No, this one I can take, this is simulation, I can take any parameters.
Right.
So here in this particular case, I took these parameters for subband 1 and subband 2 as indicated here. But I can take any other, so there is no problem with that. You form this kappa according to this transformation, and then you do these simulations. So then you see this is indeed a sort of an interesting situation when you combine both repulsive force here, if I take the gradient, and attractive force. And there is a clear-cut minimum which defines a sort of optimal vortex-vortex separation. And again, if I take type 2 regime, which is kappa effective 0.8, then normally you should expect vortex-vortex repulsion everywhere. This is indeed the case for this Q. And if you take weak coupling, then you first pair this one and then that. And of course, interestingly, you can reproduce this well-known result, what happens exactly at the crossover point, kappa 1 divided by square root of 2. There, it doesn't matter whatever coupling you take, you will get this steady minimum. All right, so now coming to the question, what parameters did I take? So it's very easy to get these parameters, band gaps, which were measured by scanning tunneling microscopy. From band gaps, you can calculate using the BCS relations in clean limit, you can calculate these two size. So basically, these are experimentally determined. And then there is a very broad range of data reported for lambda. Mostly, these lambdas were measured in thin films, and they were measured also in rather dirty superconducting materials. So therefore, what we have taken here to estimate these parameters, so we calculated lambda sigma and lambda p from these partial plasma frequencies calculated from band structure, for example, paper by Igor Maznik. So then from those I can derive these lambda sigma and lambda pi, and then if I form these two ratios, then one is indeed bigger than 1 divided by square root of 2, no big secret, but the second one may be indeed in type 1 region. So, and then according to modeling, what we expect in this mixed type 1.5 is a sort of coexistence of these two patterns, domain structure typical for type 1 with stripes of microscopic.
So it's a pure case, right? So there is no pure.
It's pure, and we see it. We scanned. So I will show the data. We scanned many samples. If you have dirty, yeah. If you have dirty limit, then this disappears. Yeah. You really need very clean, well-defined single crystals.
Victor?
Yes.
So the sort of the picture is that these vortices have long-range attraction.
Yeah.
So if you just consider that, the picture on the very right,
Yeah.
those two lines should come together. They should just form a single domain.
Could be. Yeah.
Right. That's what. So, but
No, this is just cartoon. Forget
yeah, I know.
about it.
But even in the type 1 pictures that you showed, right?
Yeah.
In reality, you usually don't see a single domain. You see it break up.
Yes, indeed.
Right?
Yeah.
So that means there has to be some other longer range repulsion in there that's not included in any of these models.
So what I considered was this basically simple Ginzburg-Landau type approach for two-band superconductivity, but of course real life is always much more complex, so you are welcome to propose something much more sophisticated.
So it's like so strictly speaking, if I have a simple two-body force,
Well, yeah, so that's,
attractive, logically possible, then stripes are not possible.
right.
Strictly speaking. And essentially, so the stripes which we have seen, like in our preliminary calculation, we created multi-body forces.
Right, but even in the type 1, the pictures he showed earlier of type 1
Yes.
superconductors, you saw that they had
Yeah, but that's very close. This is very close to this
stray fields.
crossover point.
That's what I'm saying. I
Yeah.
think that these stray fields are important in all this stuff.
Yeah, because
Especially at low
the
fields.
pattern will change if you change the thickness. It's well known.
And also
type one
even if this 3D things and all this, since it is all power law, so think power law interactions. So even in a 3D film, since we are talking about very low ordering energies in these things, so I think they are.
I'm just saying that a lot of these patterns are stabilized by a long-range repulsion, not necessarily by a long-range attraction.
I think this you can settle it between two of you. Otherwise, I will not end up on time. All right. So then schematically what you expect in type 1.5 is very well known. It's basically in type 1. First clouds to overlap are these depressions for the parameter, and then this leads to vortex-vortex attraction. In type 2, what you first get overlapping are these local fields. This leads to vortex-vortex repulsion, and if you mix these two up, you expect probably the mixed situation. So now to the experimental data. So we used single crystal, iodine diselenide, as a reference type 2 material. So you see here slightly disordered abricosal vortex lattice, but in MGB2, decoration reveals vortex-free areas which are combined with the vortex-rich areas, vortex dimers, some vortex loops, etc. And clearly this distribution is much more inhomogeneous than this one. So you can plot the distribution of vortex-vortex distances. In MGB2 you have basically three typical distances coming up together. And in iodine diselenide you have just average vortex-vortex distance. Yes?
What is the quality of the crystal?
It's a very, very good single crystal with very low concentration of defects or whatever, very narrow transition, and extremely weak pinning. So
What is narrow? How narrow is it?
You will see transition. I have one of the transitions below in my talk. So then it's clear that you have to do something. Yeah.
Between A and B.
So A and B, this is just experiment, and this is a simulation with potential which you get. So you can get these pictures if you admix repulsion with attraction.
So randomness, where from randomness come from in simulation?
In simulations, the randomness, so Charlie probably has plenty of pictures like that, and this is typical also for liquid crystals pattern formation. If you have competing forces, you always end up with that.
So you have different experiments, numerical experiments obtain different pictures.
Yeah. Yes.
It's come from the initial configuration.
So it's purely random.
Yeah.
But so there is no disorder. In the panel A and B, there is no disorder.
But the thing
No,
is that
what?
the spacing between the
There is no disorder.
Is it glass?
Disorder? No. No, there are no pinning centers here. No.
I'll just add one more.
It's intrinsic. So you have a mixture of vortex-vortex attraction and vortex-vortex repulsion, and then you end up with that.
So are you saying that it's a glass?
If I repeat, I will not end up with the same configuration. So it's from that point of glass, but it's not glass with fixed positions. So if I pull down, yes.
How is it possible that the spacing between these vortices is 100 times more than the London penetration that you showed? You have 40 nanometers.
All right. So what I'm showing here are experimental data, and I'm always comparing this guy with that guy. Whatever, you can ask many questions. So, but clearly for me, this one is different from that, and I'll show much more pictures just in the rest of my talk. I don't care. I'm experimentalist. I have two crystals. One of them is reference crystal. Yeah, that's his problem, not my problem. Sorry, guys. Yeah,
Question about
Sasha.
experiment. So the probability distribution curve does depend on temperature or does not?
So since these are magnetic decoration, so you have a crystal, you cool down, and you evaporate magnetic powder above the crystal. And then in this case, magnetic powder stacks at the places where vortices are popping up, and that's it.
So what's the resistance for this number A sample?
So the residual resistance...
No, not the residual. Does it exhibit resistance?
You mean flux flow resistance?
Yeah.
So flux flow, this is a crystal.
Is it pinned or is it what? If it's
So
not
this
pinned,
one
if it's intrinsic,
Yes.
then you should measure resistance.
No, I measure resistance by saying that I can measure hysteresis loop width. And I have mentioned already that this loop in such clean crystals at these temperatures is collapsing.
Very narrow.
Yes, extremely narrow, yes.
A couple of questions. The scale bar is how many microns?
So this one is 4. This one.
White? Okay, over there.
Yeah.
That's 4. Okay. What happens when you can't thermal cycle this sample because it's bitter?
We can thermally cycle with a scanning Hall probe microscopy. This is coming.
This is still done. Okay. Last question is, what would be the temperature at which this... So there's some average distance between them. At what temperature would lambda be equal to that distance?
So that's very difficult to determine in magnetic decoration experiments. So how do you perform experiments?
You can define a mean distance, and,
Yes.
and you know what lambda's dependence on temperature is. So
No, this I didn't calculate.
Okay.
Yes.
It's a simple question. You see, I might have missed. What are the different little details there? The
Here.
blue thing, the green
No,
thing,
it's
the
just
orange.
emphasizing that you have much shorter vortex-vortex distance, which corresponds to this arrow,
I
vortex
see.
cluster.
So
Blue
must
one
be-
is a sort of a regular average distance you expect from this field, and green one is more extended than you expect from that. But it's you can ignore these ones. It's
So
just
those are simply drawn by you.
yeah, it's by hand. Yes, if your hand is firm, you can draw.
Can I
Yes.
ask a question? If you take a more disordered than these
Yes.
two crystals, then
Yes.
probably the peak here will broaden. So is there a way to make sure that what you see on the top is not
Yeah.
simply a different strength of disorder?
Yes, for that you have to do better experiments than magnetic decoration. And I repeat, I would like to show to you this data. Okay. So then, over large area, you see again this is sort of stripe vortex pool, vortex reach, vortex pool, vortex reach, and nothing happens in the reference material, the single crystal niobium diselenite. And if you run some molecular dynamics simulation with this interaction potential we derived, then you have clustering, and then you have vortex free and vortex reach areas, and then you keep this distance in the cluster more or less the same. And if you plot the distribution of forces along this direction, then it fluctuates strongly in this case, like that, and it's practically flat in reference niobium diselenite, but you can see it directly without making this analysis. This is very nice because at a different part of the single crystal you see clearly this defect. This is step, the change in the thickness of your single crystal. And vortices are not pinned by that, and they're not correlated to that disorder. And also along that line, we analyzed the distribution of components in this particular single crystal, so it's more or less flat, and we don't have any deviations of components. So we cannot claim that these stripes are correlated with some disorder. Yes?
So what's that? I mean, is it parallel to the sample size or?
This one? No, this is a step.
No, the stripes, the vortex.
The stripe is not correlated to
With
sample
anything?
boundary, no. All right, so then scanning speed, advantage of scanning speed, you can change temperature fields, but disadvantage is that your pickup loop is in a small cryostat like that, and you have to scan as close as you can. And I think there will be special talk on scanning speed, but in low fields you still can map the local field distributions. Then you run the program, which makes the fit of this distribution, and from that you know the distribution of vortex positions, and then you plot the distribution of vortex sizes, and you see clearly that in reference niobium film, this is just single mode Rodin distribution, but in MGB2 it's clearly split. But you can see it also without doing this analysis. There is this referential vortex-vortex distances which are showing up here. So then from this fit you can extract positions of individual singly quantized vortices, and as a functional field it looks like that. So it's highly inhomogeneous, so you cannot claim that you have just homogeneous vortex lattice as a functional field. And then as a functional field, if you repeat these measurements and the fit, so for type 1.5 we have this evolution, and for slightly disordered type 2 you have this regular behavior. So there is of course quite big difference in pattern formation. Now you can analyze this vortex-vortex distance, this one and this one, as a functional field, and you expect 1 over square root of b. Would it be conventional vortex lattice? Then it goes up like that, 1 over square root of b divergence here, and these are just data obtained on these MGB2 single crystals. So now I would like to show data what we obtained here in this broad range by using another technique, which is scanning whole probe microscopy. Instead of scanning pickup loop of your squid, now at the edge here we attach very small whole cross. So this is metallization. This is the edge of the scanner. This one, these are contact pads, and this is a scanning whole cross itself. So you see it has a size typically 0.2 by 0.2 microns, made from high mobility 2T gas. Mobility is 500,000, relatively low charge carrier density, very high signal, and that's how you perform your scan. This is your sample. This is your scanning whole probe with all wires, and this is your whole cross. It's located not exactly at the corner, and that's why it's always scanned at a finite height, but this height can be reduced by tuning this angle alpha, and then you measure directly local field distribution by this scanning whole cross. The typical distance between STM tip and whole cross is at the angle of 2, this height is typically less than half a micrometer, and field resolution is quite high and can be improved if you introduce also modulation, AC modulation of magnetic field. So this is transition, so several of you asked to show this transition on this single crystal, so it's really quite sharp. And this thermal cycling is related to some problems with the heater, where it's played with respect to a thermocouple and thermometer, but the transition itself is quite sharp. So now the experiment which was already asked about, what will happen if you have disorder due to random distribution of strong pinning sites. What can you do? How to check it? You do several run-ups to cool down. You warm up above TC, fix the field remains exactly the same, and then you cool down.
This distance between vortices,
so
interaction has a definite sign, right?
Yes.
So where is this frustration coming from? Why?
So stripes, this is coming from competing interactions. Because if you have type 1.5, then one subcomponent is in type 1 regime, and it promotes...
But if distance between vortices is much larger than both coherence lengths, then interaction is positive, right? So
if it's much bigger than that, then it's, of course, here, right? Exactly. Yeah.
So on this curve, this white region is weighted.
This is where you have a vortex, so this is local.
So this white region is a radius of coherence length, right?
This one is not coherence length. It's not scanning tunneling, it's scanning hole, lambda.
Fine. So coherence length could be 2 times larger, right?
Of the order of, if you wish. Yes.
10 times?
Yes. It depends on the temperature. It depends on the temperature. So I can measure.
Give me just feeling. So in
this could be a couple of microns easily, several microns. But if you come closer to TC, then you see that the contrast grows at this temperature. Yes, it's quite close to TC. That's what I'm saying.
Let me make one reservation.
So if I warm it up, I can watch how this white spot is increasing in size. And when I come to TC, it disappears, the complete point.
Let me actually make one reservation. I wanted to talk about it, but I didn't.
Only a short comment is allowed. Okay, you go.
So essentially, so when one has various couplings between condensates, so one should be very, very careful with how one defines coherence length. Because
I understand.
So essentially, the normal modes are no longer individual fields, but they are some combinations.
All right.
And so it could be that.
But still,
that's clear.
That you can have 10 times larger than basic coherence length.
No, it's 1 divided by square root, 1 minus t divided by tc can be any number, as far as I know, including infinity. Okay. So if you have a very clean single crystal with transition which is extremely sharp.
What is your mean free path?
Here,
Yeah.
it's a few thousand of angstrom. So in this case, I'm showing now field-cooled experiments at this temperature, 4.2, and the applied field was 1 Ørsted. So then you see these are not really filtered or whatever the data as we've got. So you see it's more or less random, but not at all, because you see here already these stripes are nicely formed, this one, and this one. Then of course you can do the same experiment. You warm up again about TC, you increase magnetic field, now it's second field cooled in the same field, and then again to answer your question, I'm sure these are not strong pinning centers. If I compare this picture with previous, I do have some areas which overlap, but in general, positions are not the same. So if I make exactly the second cool down, I will never get the same pattern if I don't have strong pinning. All right, now I'm increasing magnetic field.
Quantify that with a correlation?
With what?
Some kind of correlation function.
No, I don't have that statistic with me. I cannot answer your question. So now we are increasing magnetic field, so we apply 2 Ørsted. So vortices can go any place, here, 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 if it's typical type 2, but they do not. They like to form these stripes, whatever the reason for that is. So if this is not the stripe, then I'm certainly Napoleon. Okay. So then you increase again magnetic field, 3 Ørsted. You have again vortices like to sit more here, closer to other vortices. And then these are much brighter. So I suspect these are giant vortices. So vorticity of this vortex is bigger than 1. So we have, and this one we have to look into. So, but the main message from these measurements is vortices do not like to form abricosal lattice here, although pinning is very, very, very low. Now I'm going to 4 Ørsted. Okay. And at 4 Ørsted, it's again the same story. That guy which had giant vortex is probably also, but very nicely defined vortex chains or vortex stripes. And when the second stripe is close to the first one, you see nicely this zigzagging. Okay. Then you may have some layers like here 3, here also 2, and this is the third row, etc. So we have plenty of these measurements. So these data were taken in December. Yes, I'm showing raw data. Yes, question?
These are all taken on the same location.
These are taken on the same location.
If you take all the positions from all of them and overlap them,
yes,
it goes to completely homogeneous.
So if I recycle with temperature, right? So I can warm up, cool down again, exactly the same field. That's what I'm saying. Then I have
different fields, just overlapping all the positions. It comes out completely random.
This is more or less indeed if I do. It doesn't make any sense, but if I overlap what you are saying, this will be, the whole field will be covered. But in each individual image, I will see these different stripes.
Could you tell us what HC1 is?
So HC1 here, so this is a thin film, so you have to be careful with the demagnetizing factor. So the HC1 is some fraction of Ørsted here.
Is it just an optical?
Because of it's a very thin platelet. It's not really a sort of Yeah.
Is it just an optical illusion, or is some of the bright spots also?
It's not optical illusion, that's what I'm saying.
As well?
Some bright spots probably correspond to giant vortices. So this I can tell you by integrating this area. I know local fields, so I can determine the flex. So, but from experience with the periodic pinning, we do know that if you have bright spots like that, it's a signal that you have giant vortices.
Yeah, but some of those spots look, to me, elliptical rather than round.
Ooh, this is, this is difficult. For example, this is a cutoff here of the field. You see, this was field of view, then another one like that, and then you overlap that. So this one is a defect of the image. Don't pay any attention to it. But also you can drag vortices. This you can do. All right, so since my time is out, so we have tried to visualize vortex matter in these materials which we call type 1.5 superconductors, and we did use 3 different scanning techniques, 2 scanning techniques and 1 magnetic decoration, and we do have experimental evidence that in this area, just after the Meissner state, the formation of vortex patterns is highly unusual in single crystals with very, very low pinning. So I stress once again that it's actually observed. So conclusions, type 1.5 superconductors, possibly clean NGB2, possibly these S1, S2 hybrids, if we make them like sandwich structures, and clean this one, but it looks like this one is not. So although it has 2 gaps, but it's not in this region. So the combination of vortex-vortex repulsion and attraction in the same material leads to the appearance of these competing interactions. They always give you very unusual vortex patterns. You get gossamer-like patterns, clusters, stripes, etc. And we used squid microscopy, bit decoration, and also scanning whole probe microscopy. And modeling of these patterns actually can be done by molecular dynamic simulations, no problem. You just take potential which combines repulsion with attraction, and then you can reproduce this data which I have shown. So what next? So for actually 2-band superconductivity, probably the first microscopic evidence was given by 2 Nobel Prize winners, although at that time they were not yet Nobel Prize winners, but they did a very careful measurements of niobium deposited on strontium titanate, and then you clearly see here 2 gaps, and they followed also the evolution of these 2 gaps with temperature. For example, this is beautiful old work, and even older, 65. So if you go to this Norman Phillips publication, so he was claiming by measuring heat capacity, so you expect, according to the BCS theory, single exponent decay of heat capacity, but they always see sort of 2 tails, and they were claiming that this is 2 energy gaps in this material, but that was motivated, of course, by this original paper, 59, about 2-gap superconductivity, Harisu with co-authors. And this is another beautiful example, recent ternary compound, lutetium-2, iron 3, silicon 5. So heat capacity is a function of temperature, a very nice 2-gap fit. And the gaps are quite different, but I don't know in clean limit whether this material can qualify for type 1.5. That's another 2 gaps in these iron pnictides. And finally, we are working currently with these artificial layers. When we take type 1 substrate, we make an insulating layer and we deposit on top type 2 superconductor, and then we are scanning these patterns. So thank you very much for your attention.
There will be a discussion session on Saturday. So I'm sure Alex has a lot to say as a specialist on diborite. So welcome everyone. That will be after the talk of Mikhail on microscopic theory of monotonic vortex interaction, low temperature theory of type 1.5 region from physical invariant theory. So I welcome everyone to the discussion session. So maybe we have maybe can take a couple of questions.
What is the size of the critical current?
So for us it's very difficult because these are tiny crystals, so typically 50 by 50 micrometers. So we didn't attach to them any contacts, and when we measured hysteresis loop at temperatures we used, it was really collapsing. Yeah. So from that I conclude that critical currents were very, very low. But I didn't measure directly them in transfer on this single crystal.
Questions?
Okay. The wall already.
The sample at the beginning, is it like a substrate? Is it film or is it bulk sample?
All of them are bulk single crystals. In thin films, mean free path is much shorter. Then you end up immediately type 2 regime for both some components. No way. You need high quality single crystal.
For magnesium diboride, when you show the voltages lining up, do you have any field perpendicular parallel to the plane?
Yeah, that's a very good question because that paper published by Sasha Buzdin was made when he was in my lab in Moscow. So we were very much aware of this tilted vortex problem in anisotropic superconductors. So we did this tilting. No way to get rid of this. It's the same. So the stripes are not correlated with any possible tilt.
And maybe I just like to make a very short remark regarding Boris' question. So that's relating to bare core size, like if you take 0 Josephson limit and again congruence links, it's extremely tricky. For example, if you consider interband impurity scattering, then there is an effect which is exactly analog of seesaw mechanism in neutrino physics. Phenomenon neutrino physics, there is seesaw mechanism where you have two masses. And then through seesaw mechanism, one mass goes to high scale, another gives an anomaly the low neutrino mass. So this is called seesaw, that's Kacelli inversion. So there is, for example, in multi-band theories, there is an analog of, for example, this kind of mechanism. So this like, and it could be that near the core, all the parameters behaving almost the same, and then both density fields they have very, very long density suppression, very unusual length scale. So it's so let's move to the next talk. So it's a great pleasure to introduce moshchalkov+maeno from Kyoto University.
Thank you. I'd like to thank the organizers to give me the opportunity to visit Sweden for the first time. And this is the recent work, topological junction, interference between even parity superconductivity and the superconductivity of strontium leucinate. This is the topic I was originally thinking of giving. But Igor wanted me to give you introduction to the superconductivity of strontium leucinate, and also include some brief review of vortex physics in strontium leucinate. So after arriving here, I worked hard, fighting against jet lag, preparing another talk, which I'm going to give for the first time. I'm not a specialist of vortex physics, but so I really appreciate Igor giving me the opportunity to review those lots of efforts done by many people. in the last 50 years for the vortex physics of strontium-2-ruthenium-4. Okay, so this is the new title of my talk, Quantized Vortices in Strontium-2-ruthenium-4. So in the first half, I will briefly tell you what the superconductivity, what we know about the superconductivity of strontium-2-ruthenium-4. And in the sort of three topics, it's a spin triplet superconductor. It has a two-component chiral order parameter, and it has multiband superconducting properties. And then the second part, I will give a brief review of what's been studied concerning the vortices. First, the individual vortices. Okay, what we know about each vortex. And then vortex coalescence. This is relevant to what Victor just gave. And then flux line lattice. So those, and I will summarize. We just started our national project, 5-year national project called Topological Quantum Phenomena. So we have some English web page ready, and we will have some international conferences coming up. So this project, we combine spin triplet superconductors, superfluid helium, and topological insulators, surface physics, hot frequency superconductivity, and so on, those exotic phenomena. Okay, so this is the crystal structure of strontium-2-ruthenium-4. This has the same, actually this is the first superconductor discovered with the same crystal structure as the high TC cuprate, but without copper. And we are fortunate to discover this superconductivity many years ago, 16 years ago, 17 years ago now. And it has a TC of 1.5 Kelvin, and it's a weak coupling type 2 superconductor. And the Ginzburg-Landau parameter for the field along the C-axis across interlayer direction is only 2.6, rather small. And in the plane, the Ginzburg-Landau parameter is about 40. So, and we can grow a big single crystal. This is 1 centimeter, so this is like 8 centimeters by this method. And it has a very weak pinning. So by AC susceptibility, we know that the vortices move very, very easily. Okay. And the residual resistance in the plane is 0.1 micron centimeters, which corresponds to the mean free path in the plane of about 1 micrometer. Okay, so it's a very clean system. So this is the list of basic parameters, superconducting parameters. Hc2 in the plane is 1.5 Tesla. And it has the gamma, the anisotropy ratio of 20. So for the field in the C direction is 20 times smaller, 750 Gauss. And the coherence length deduced from Hc2 using the orbital limiting assumption is 660 angstroms in the plane. And across the C-axis, along the C-axis, it's 33, which is 5 times bigger than the interlayer spacing. So it's not a two-dimensional superconductor. It's a highly anisotropic, three-dimensional superconductor. And then kappa, as I mentioned, it's 2.3, 2.5, rather low for the field in the plane. Okay, so this is a field in the plane where the xi and the lambda of AB plane become relevant. And for the field in the AB plane, we have 46. Okay, so there are very many reviews written on strontium-2-ruthenium-4. So I and Andy Mackenzie wrote a while ago, this 78 years ago, tutorial overview, which we intend it to serve as a textbook for graduate students. And then if you're interested in the microscopic mechanism based on Coulomb repulsion, Yanase and Nomura's Kosaku Yamada's group has this review. And then Manfred Siegrist talks about the chiral P-wave state, and then Kenji Ishida has summarizes NMR results recently. Okay, there are a number of new ideas concerning superconductivity emerging from the study of strontium-2 ruthenium-04. First, Rice and Siegrist wrote this paper, quasi-two-dimensional analog of superfluid helium-3. So actually this order parameter is very similar to that of helium-3 A-phase, although this has a rather nice two-dimensional film surface. And so quasi-two-dimensional analog of helium-3 A-phase. And then people have talked about this multi-band superconductivity. Initially, the Achterberg, Rice, and Siegrist called this ODS, orbital-dependent superconductivity. So this idea has been adopted, as we saw, to magnesium diboride and iron nuclides later. But the idea discussed concerning the superconductivity of strontium-2 ruthenium-04 is a little earlier. And since the multiband has different orbital characters, they can have different gap structures. I think those are quite important, not just the size of the or intrinsic TC of each band, but they can have different gap structures. Right? And then this orbital dependence has been, the idea has been extended to the mode transition, band-selected mode transition, where different bands stay multi-insulator and the other one become metallic. So. And then time reversal symmetry breaking, chiral superconducting state. And for the mechanism, I said Coulomb repulsion induced superconductivity. This goes beyond the spin fluctuation, which is second order, and this goes beyond the second order term to explain the Cooper pairing. Okay, then for the field-tuned quantum critical point, there are a number of sister compounds, and strontium-3, ruthenium-2, O7. We have we apply the magnetic field, and the metamagnetic transition shows quantum criticality and the nematic electronic phase, and those are also studied in other systems. Okay, so what we know, to summarize, what we know about the superconducting state of this material is, okay, this is a cartoon of a Cooper pair. So these two balls are electrons, and these colorings are electron spins. So this has a spin triplet. So when this electron has a spin in this direction in red, the other one, the pair, also has a spin. So it's a spin 1 description cartoon of the state. And this D, we use the order parameter of spin triplets superconducting state, D vector. And D vector is has a spin component and orbital wave function. And this spin state, Z means just SZ equals 0. SZ equals 0 means spin up, down, plus down, up, right? So that means spin 1 pairs are in the plane. So this is superposition of spin up, up in all directions in the plane, so that we have no component in the Z direction. So if you choose the quantized axis in the Z direction, we call this up, down, plus, down, up. Right? Okay, so, and NMR night shift and polarized neutrons night shift show this is a spin triplet. And then for the orbital states, there are many experiments, and these are consistent with the state of kx plus iky. This is nothing but the LZ equals 1 state. So this Cooper pair, 2 electrons are revolving mutually. in one direction, so that the orbital angular momentum, which I depict here in blue, is pointing in one direction. Lz equals 1 or Lz equals minus 1. So it spontaneously breaks standard reversal symmetry. And given the superconducting domain, all the Cooper pairs within this superconducting domains are all revolving with Lz equals +1, or you have a different domain having Lz equals -1.
Is the direction of the spin, is it tied to the direction of the angular momentum? In other words, can spin have zero projection but on some other axis?
I'll discuss this because there are several mechanisms to orient the spin direction, orient the spin. And okay, so the conclusion is experimentally and theoretically it's not clear yet. So I'll give you some ideas.
So it is not true to say that it's simply crystal anisotropy. Can one say that it's simply crystal anisotropy fits direction of the quantization?
The L vector, this orbital angular momentum is quite well fixed because of the in-plane, the quasi-two-dimensional.
Two-dimensionality.
Yes, quasi-two-dimensional, conduction plane. So L vector is fixed. Okay.
But
now,
spins are
what about spins? Okay, right. So there are many mechanisms which try to align spins in the plane and also out of the plane. And those several mechanisms compete with each other. So theoretically, it seems it's very difficult to really predict precisely.
But all of them are connected with crystal anisotropy, or not necessarily? All of them, in fact, originate from crystal anisotropy.
So dipolar interaction and atomic spin-orbit coupling and spin-orbit coupling in the orbitals. So these terms has a plus and minus and similar magnitude, and theoretically it's not very easy to really predict. An experiment I'm going to talk about.
There is no SU2 spin symmetry here. So
spin symmetry.
There is no, you say in the end it will be chosen by terms that break SU2 spin symmetry, spin orbit terms.
See, I don't understand the exact word, but let me go on and then I'll show you the experiment and the interpretations.
But maybe that's getting a little bit ahead, but is it possible to have half-flux vortices?
Yes, I'm going to talk about it. Yes, I'm going to talk about it. Yes. All right. So this, anyway, I'll talk about this. I'll say that this is a topological superconductor because this state, kx plus iky state, is kx is like p wave is like this, and this is another p wave, and this is kx plus iky, so which is just exponential I theta. So this means the phase phi here is nothing but the direction theta. So if you go around, the phase changes. So that's also topological superconductivity. So originally, so I'll skip this one. I just explained it. Kx plus iky is nothing but this one, y spherical harmonics, Lz equals +1. And then this one has this d vector will give you essentially fully gapped state, no line node.
Wait, is it the same as, so when you talk about the spin polarized p-wave superconductor, then you're right, it's completely topological because the phase is all there is, but as I think Victor alluded to, if you have a d vector now that can change direction, you can, is it still topologically the same? Because the one phase is not all the great freedoms that you have.
Let's see, this is just orbital wave function. So orbital wave function has topological properties.
So will it have Majorana fermions in
this half-flux vortex will have Majorana fermions. This is looked at. So
the half-flux.
I'll go into the first part of the second half is I'll talk about half-quantum vortex. So I haven't got into this first part of this. Spin triplet. Okay. So we have this NMR evidence. I'll just go. So the spin susceptibility is invariant across TC. On oxygen site, 2 oxygen sites in the plane, and the ruthenium also doesn't show it. And this is unlike heavy fermion superconductor. This is the transition metal elements, and spin and orbital are quite, the susceptibility are quite well separated. And then, so we know that the spin susceptibility doesn't change.
So you mean the spin orbital separate, not coupled? The spin orbital is
yes, right. However, if we do this
experiment, so you have a picture, the d vector lines up with the angular momentum, but the spin is also in the plane. So what is this arrangement if the spin is not
yes. So the important, experimentally important thing is, now this what I showed is all the magnetic field in the AB plane. So if you apply the magnetic field in the AB plane, the spin 1 spins can polarize. Okay. So, but if the spins are fixed in the plane, then if you apply the field in the C-axis, then since there is no spin component along the C-axis, just like S-wave, spin susceptibility should decrease. So that's the prediction. So here, for S-wave, for any H direction, spin susceptibility goes to 0. For the P-wave, if you apply the magnetic field perpendicular to the spin, so Sz equals 0, so if you apply the field in the Z direction, it should go to 0. Right. But experimentally, we did it in both cases. This happened. Okay, so that questions this original interpretation of this d vector pointing in the C-axis. D vector is defined as the plane perpendicular to the spin. Okay. D and the spin are perpendicular to each other. So there is a microscopic theory also putting emphasis on the on-site Coulomb repulsion from the oxygen predicts that d vector should be in the plane instead of out of plane. So this is the original one, and this is another interpretation. And in this case, the spins are rotating in this plane. So in any direction of magnetic field, the d spin can polarize. So this is another possibility, a promising possibility, and theoretically allowed. So, but we haven't had any final conclusion. Okay, so chiral order parameter is μSR shows internal magnetic field below TC. I'll just go quickly. And then somebody talks about the edge state. Baratsky Sasha talks about this. So when you do the tunneling experiment, for YBCO, you have this zero bias conductance peak, Andreev bound state appearing in the energy much smaller than the gap. But for strontium leucinate, this bound state has a really large energy compared with the gap. And this can simply explain that for YBCO, this in the gap, the edge state is just non-dispersive Andreev bound state. Whereas for the strontium leucinate, there's a chiral edge state. So this is the direction is in one direction. So there's no branch in this direction. So this broad peak can be explained that in the gap you have a chiral edge state. So that's well, after many measurements, many interpretations, this is the clean picture. And then topological superconducting junction, that's what I'm going to discuss, but I don't have time. I just give you the flavor of it. So if you surround the S-wave superconductor by strontium leucinate, then measure the critical current between S-wave superconductor and surrounding strontium leucinate. Then what happens is it's a lead, JC goes up, and if strontium leucinate becomes superconducting, also JC goes down and then goes up again. So it's a very strange behavior, robust. And this is another junction, and we can explain this in terms of the phase winding of the P-wave superconductor going from n equals 0, matching with the S-wave, with n equals 1, which is disturbing, the interfering with the S-wave. So just to give you the flavor, I was going to talk about this for the entire talk, but it's quite complicated. So multiband superconductivity. So strontium leucinate has a multiband. How am I doing in time? Maybe.
Yeah, it's fine. Yeah. So it's, there's no strict restrictions.
Ruthenium. So when did I start?
I told the restaurant to wait us.
That's okay.
So ruthenium has 4 plus state. So it has 4 d electrons. So for d electrons, you have 5 levels, and then you have 4 electrons. So you fill 3 levels with 4 electrons. Okay. So these 3 levels are dxy, dyz, dzx, and dxy forms a 2-dimensional network, and dyz, dzx forms a 1-dimensional network with the oxygen. And this is the experimental observation of the Fermi surface by quantum oscillations. So this dxy, the in-plane 2-dimensional orbital, this gamma. And then alpha and beta comes from originally this 1-dimensional Fermi surface. So this is alpha also giving this same Fermi surface. So we believe that gamma Fermi surface is the main superconducting band. And alpha and beta having different character, quasi 2D, quasi 1D, different character has induced superconductivity by proximity effect, K-space proximity effect. It has a smaller gap and different gap structure. And this is the quantum oscillation. So you have alpha, beta, gamma, and we have a beta large splitting because of a minimum maximum area, and this mass determination for each band. If you add up these mass for 3 bands, you reproduce the specific heat electronic coefficient really well quantitatively. And then if you measure the specific heat, please just note this curve. If you apply the magnetic field in the plane, then so that the coherence length across the C direction becomes important, then at a rather small magnetic field, so HC2 is 1.5 Tesla, but at low temperatures, at rather low magnetic field, some of the band is already filled with quasi-particles. So you have some part of the gap is easily destroyed by the magnetic field. And this is corresponds to, this gamma corresponds to that of density of state of alpha and beta. And this total is alpha, beta, and gamma. Yes?
Do you subtract phonon term from here already?
Which term?
The phonon.
Phonon, yes. Phonon specific heat has already been subtracted, yes. Since Tc is quite low, it can be easily done, and also the contribution is small. And so low Tc really helps us to analyze this quantitatively. Right. Okay, so this behavior is called orbital dependent superconductivity. Different bands can have different gap structures. Right. So, and this is the theoretical prediction based on this 3-band model, 3rd-order perturbation theory of Hubble band, and this active gamma band would have this gap structure, and then passive alpha and beta, you see that the minimum of the gap is in a different direction. And then this is the specific heat data analyzed in terms of this model. And then we actually have this using Borovic effect. You apply the magnetic field in the plane and rotating, and you see this specific heat oscillations from which you can deduce the location of the minimum of the gap, which is consistent with the theoretical prediction.
So usually this data do not point to any nodal kind of lines or points.
Experimentally, we cannot tell whether this is a small gap or the node. This is just the density of state measurement.
But it would be the node, which way it would point?
So the this 1, 0, 0, where the Van-Hoff singularity, where the gamma band gets very close to the Brillouin zone boundary, the gap is small. So this is consistent with this.
But there is no neck in only
So
TZ.
you can say whether it's P plus IP or what? So your last domain.
Yes. This is a KX
Can it be
plus.
translated that actually whether it's P plus IP, which is fully gapped or not, is not clear?
So it's yeah, I'm going to talk about this very soon. Yeah, at the end. Just whether this is a sine kx plus I sine ky or sine kx plus ky plus I sine kx plus ky. Okay, so those issues. I'm going to discuss this. Yeah, it becomes important when you discuss the square lattice, vortex lattice. Okay, so the second part. Okay, individual vortices. Okay, so for the scanning Hall probe by Stanford group, they mapped out this. They probe this individual vortices, and so this is the individual vortices at low temperature and very low magnetic field. And actually, there are this dimple, sort of not the through hole, but some dimple drill in this separation. I don't know the location with respect to this observation, but so there is no pinning in around here. So there is no indication that the vortices are pre-pinned in this small hole. And anyway, so I didn't mention this, but theoretically, Kato at the early stage, he discusses the stability of different kinds of single vortices, not the half quantum vortices. But you see, Cooper pair has Lz equals +1 or -1. And when you have a vortex, this Cooper pair moves clockwise or counterclockwise. So you can have 4 different vortices, right? Combination of the current, the vortex sign positive, and the Lz of the Cooper pair also positive. So parallel configuration or anti-parallel configuration. So he discusses the stability of this. And experimentally there has been no identification of these different vortices. Not yet. All right.
But
so,
in this case, difference between two vortices only inside of the core. Outside of the core difference. That's why probably it is difficult to detect.
The core shouldn't have the
difference only in the core.
Only in the current revolving around the core. So the sign of the orbital current and the sign of the L vector of the Cooper pair, that can be parallel or anti-parallel.
Yes, but it is important only inside of the core, or you don't think so? Because
core,
outside, at large distance, it does not matter, up or down. Is it so? Maybe I don't know.
Well, given the superconducting domain, all the Cooper pairs have Lz, say positive, okay? Then you apply the magnetic field positive direction, then Cooper pair L vector and the sign of the orbital current is the same, or you can have an opposite sign. Is there any difference in physical properties?
Yes, there
There
is.
must be.
The line energy of the two vortices is different, and that produces an asymmetry in the lower critical field for nucleation. The vortices that have their vorticity aligned with the chirality or anti-aligned with the chirality. So the issue would be a direct.
There may be a sort of targeted experiment which can be done, but no proposals, no experiment.
Well, the proposals would make that.
Okay, yes, that cutoff, or maybe there are other. So this review is quite brief. I mean, I cannot cover all the references in this time. So another brief review of half quantum vortex observed in this system. Okay, this will appear in Science next week, or 2 weeks later. This experiment was done by Illinois group, Rafi Budakian's group, and also Paul Goldbart should show up tomorrow. Oh, is he here? No. Okay. So there, and then some crystal is provided from Kyoto University.
Quick question. So, well, maybe on this. So, can you only observe the half quantum vortices in the rain? You can't observe them in the bulk?
No. Right. So, where to look for half quantum vortex? Okay. So, full regular quantum vortex is more stable. And that's because half quantum vortex is associated with the spin current. The energy of the spin current costs energy. Right. So it's not stable. So you need to look for a location or condition where half quantum vortex energy become smaller. Okay.
But so, can be isolated, or it should be connected with domain wall.
Yes, a small domain wall can cut the
line which is border of the domain wall. Is it so? Okay.
In principle, yes. And also the pair of half quantum vortex will cancel this spin current energy, and that's also a possibility.
But would a hole in the sample do it?
Yeah. I'll show you this in a moment. Next slide. But just to show you, for those who are not familiar with this, for ordinary superconductor, to keep the single valuedness of the wave function, you need a phase winding of 2 pi, and you have a flux quantum. For spin triplet superconductor, you have a spin degree of freedom and orbital degree of freedom. And the orbital degree of freedom is what couples with the magnetic field, with this 1/2m gradient plus I vector potential term. So if you have an orbital part only winding of pi, and then spin part taking care of the other pi, then you recover the 2 pi, the wave function which does not interfere with yourself. Okay. So this is the d vector. So the spins of the Cooper pairs are perpendicular to this vector. So it's in the plane, spins are in the plane, and then you rotate around this core, and then this spin plane rotates, and then you come back like this. You start with this, you come back with this. So physically it's the same state, spin in the plane, but with the phase pi different. Okay. So physically this is happening. So then in this case you have orbital is only pi, so you have half quantum vortex. Okay, but the phase of the orbital will create charge current, and this tilting of the d vector will create spin current, and you have a spin current energy associated with it. And so supposedly to cut this spin current energy, you need a restricted geometry. And so what Rafi's group did was to make this crystal. So we sent this a big crystal, 1 centimeter, 8 centimeter crystal, and they really hammer it to 1 micron size, and drill a hole of 0.5 micron, and that's this small crystal. And then this is a cantilever. They measure the torque under the magnetic field, from which they deduce the magnetization of the ring. So this is the data. With under external magnetic field on the z-axis, you have a regular integer flux jump. And then if you apply additional in-plane field, and then this is a Meissner component is subtracted, then if you have additional in-plane field, then you have exactly at the half the magnetic field, you have half the magnetization jump. So this is a very hopeful evidence for a half fluxoid state.
Characteristic size, for example, measured in lambdas. How many lambdas do you have?
Lambda is say 2,000 angstrom, so 0.2 microns, and the size of the crystal is 1 micron with a 0.5 micron hole in it. So the thickness is comparable to lambda. So there's the Meissner current is flowing everywhere. So it's the fluxoid, not the flux, which is quantized here. Okay. And then for a possible explanation of why in addition to the c-axis field, why the in-plane field was necessary, the Leggett and Bakalyuk has a theory, so only applicable to half quantum vortex state. As I said, for half quantum vortex state, spin up and spin down species has a different winding. Okay, so I said the spin has a d vector has rotation and spin has a pi winding, but you can interpret this the same physics, same phenomena, having spin up having zero winding, and spin down having winding of 2 pi. Okay, so that means you have a different velocities, and then you have a different kinetic energy. So this introduces a new mechanism for spin polarization. So that's why one interpretation is that's why this additional field stabilizes only the half quantum vortex state. So vortex coalescence. So I'll show you 2 figures for experiment. This is Stanford group. So when you apply this field in the c-axis, you have these vortices. I showed the same figure before. If you increase the field, then the vortex seem to sort of align. Okay, it's not so clear. And Ichioka has a theory explaining this alignment may be something to do with the boundary of the chiral domains. And he has some simulations. Okay. Then French group, Hasselbalch and Dolocan has these experiments in which they can control the c-axis field and AB plane field. And they observe 2 kinds of vortex coalescence. And first is lining up vortices. In the field cooling, this is nearly HC1, this is exceeding HC1 with the field in the AB plane, and then you have another field, fixed field along the c-axis. So you see these vortices. You cannot resolve each vortices, but the vortices are in this direction, but aligning in the line. And they say that this line, direction of this line, is in the direction of in-plane field. So if you rotate the in-plane field, this line will rotate. And then they observe another kind of vortex coalescence, and that's they call it crossing vortices. And this is for the zero field cooling, and then they apply the magnetic field after in the superconducting state, and they see this. You see this bright and dark areas on top of this line. So they interpret this as something like this, crossing vortices happening. I don't know. This picture.
In panel A, when there is no in-plane field, how robust are these vortices? Do you know that they try to move them, or?
Yeah, I don't know. There are some residual magnetic field in the system which causes these vortices, sort of clustering. Not really lining, but clustering. Yeah. So I don't know. This is the paper by French group. So okay. So as soon as this in-plane field exceeds HC1 of in-plane, these well-ordered structure is formed in this particular system. So there's qualitatively some difference between this system and type 1.5 superconductor. So the mechanism may well be different. All right, so I'll come to the final part. The flux line lattice. Okay, so the square lattice is observed. Neutron diffraction. This is for the field in this along the c-axis. Okay, field along the c-axis. You have instead of a triangular lattice, you have a square lattice. And when you read this paper, Nature, please be careful that they have a correction later. The assignment of the direction of the crystal was different, was wrong. Okay, so actually the square lattice is along the diagonal direction for the real space crystal, whereas the theory predicts orthogonal 100 direction. So it's some inconsistency. So this is the experiment.
So never they observe triangular lattice.
Pardon?
Is it possible to observe triangular lattice?
No. This has only square lattice observed for the field along the c-axis. It's a tetragonal system, and so theoretically this square lattice is predicted, but the direction of this, orientation of this square is it has a controversy. And so it depends. It turned out it depends on the wave function. So there was a question earlier from the back. It's, whether this is sine kx plus I sine ky. So this has been used. But then depending on the microscopic theory, this is also possible. And the difference is this has in the m direction the gap is small, but in the diagonal direction gap is large. Okay, that's the same. But in addition, in the x direction there is additional dip in the gap. Okay,